Today we'll be starting Chapter 6, Modeling Random Events, the Normal and Binomial Models. To start with, we'll look at Section 6.1, Probability Distributions are models of random experiments. So in previous chapters, we studied distributions for both numerical and categorical variables. And the following is a distribution of ages for the players on the New England Patriots in March 2016. The distribution above gives us the ages of the players on the team as well as the frequency of players at each age. Another way to display this distribution is in a table. So we're saying that if this is age 22, we have 8 players with the age 22. We can see this down below in the frequency table that we have at age 22, we have 8 players, and we can sum up this column here, and if we added them all up, we would see that we actually had 79 players that we're looking at, and that's given to you up here where the count is equal to 79. The distribution of ages for the players on the New England Patriots can also be displayed using relative frequencies for each age. A relative frequency gives the proportion of the team with each given age. In other words, the first bar now is rescaled, showing that 8 out of 79 is equal to about 0.1. And so the relative frequency you can see here. This can also be shown in a table of relative frequency down here below. So this first row is saying that 8 out of 79 is equal to 0.101. So what is the probability that a randomly selected player is 26 years old? So we need to go up to our table and look at row 26. 13 of the players are 26, which would mean that the probability would be 13 out of 79, which is equal to 0.164. Or 16.4%. Probably should round up to actually 16.5%. What is the probability that a randomly selected player is less than 26 years old? So less than 26. So that's going to be everybody that's under the age of 26. So in order to figure that out, we would need to actually sum up 8 plus 9 plus 9 plus 10 over 79, which is equal to about 45.6%. And what is the probability that a randomly selected player is greater than 26 years old? Again, we're looking at several rows, all of the rows that would be greater than 26. So we need to sum up, well, we have 2 choices. Actually, we could sum up all of these numbers, 9 plus 6 plus 3 plus 5 plus 3 plus 3 plus 1 to figure it out. Or we can know that 79 players are the total. Minus the 36 that we found in the previous part, and minus the A13 that are 26 years old. And so that comes out to be 30 over 79, which is equal to 37.97%. So we remember that the total would add up to 100%. And so this last piece here would be all of the players minus the other two groups we already looked at. In this chapter, we are going to learn about probability distributions, which tell us about the possible outcomes of a random experiment and the probability that each of those outcomes will occur. If we consider selecting a player at random from the above table, then the relative frequencies give us the probability of selecting a player of a given age. So in other words, the last table that we looked at on the previous page is really a probability distribution. A probability distribution is sometimes referred to as a probability distribution function, or PDF. So the following, I'm looking at number 4 here, the following is the probability distribution for flipping a fair coin. Notice that this distribution shows two possible outcomes. You can either flip a heads or a tails, as well as the probability of each outcome. Since the coin is a fair, probability of heads is 0.5 and the probability of tails is 0.5. So here we have heads coded 1 or tails, which is coded 0. And both have the relative frequency of 0.5. So this distribution can be shown either form below, which is a bar graph is on the left, and then also the book shows with the lines coming up to the probability of 0.5. The probability distribution can also be given in table form, and the table for the above probability distribution is given below. Notice that the table tells us all the possible outcomes. So we have, these are all our possible outcomes here. We either have a tails, which would be coded 0, or a heads, which is coded 1, and the probability of each outcome. The following is the probability distribution for rolling a fair six-sided die. Notice that this distribution shows the 6 possible outcomes, which are 1, 2, 3, 4, 5, and 6, as well as the probability of each outcome. This probability distribution can be shown in either form again. So similar to what we just saw, we have a bar graph on the left. So the outcomes are listed across this horizontal axis, and each of their possible, their probabilities is given here. And so each one of these has a 1/6 chance. And so you can see that probability by the height of the bar. Again, we could use a table. And notice that this table tells us all the possible outcomes. So that's in the first column, all possible outcomes, 1 through 6. And the probability that corresponds to each outcome, again, 1/6 or 0.167. This distribution, this probability distribution that we're looking at, is a theoretical model, okay, of what would happen when a fair die is rolled an infinite number of times. So it's not actual data, but rather the theoretical model of rolling a die. Does the theoretical model do a good job of predicting what will happen if we actually roll a die 1,000 times? I used StatCrunch to run a simulation since I didn't want to actually roll a die 1,000 times, and here are the results of the simulation. So over here we have our frequency bar graph, which is the number of times you can see that you rolled a 1. Looks like maybe 155 or so times. And then over here you have your relative frequency bar graph here, and below a table of relative frequency. So, and then we would wonder, according to the simulation, what's the probability of rolling a 3? So looking at this, the probability of rolling a 3 is about 16.8%. According to our theoretical model, what's the probability of rolling a 3? That's 1/6, which is equal to 16.7%. And the question we want to know is, did the model accurately predict what would happen in our simulation? And we could say, yes, it's pretty close to the simulation results are pretty close to what we predicted using our model. So in chapter 1, we classified variables as either numerical, like ages, or categorical, heads or tails for a coin. In this chapter, we need to further break down numerical variables. So we're focused on numerical variables, and now we're going to break those further into 2 more categories. The 2 categories are discrete variables and continuous variables. Discrete variables have numerical values that you can list or count, versus the continuous variable are numerical values that cannot be listed or counted because they occur over a range. So 2 of the previously discussed variables are examples of discrete variables, whether a coin lands head or tails. So if the outcomes are coded as 0 or 1, we can call this discrete. And the result of rolling a fair die, the outcomes are 1, 2, 3, 4, 5, and 6. And so they're countable and discrete. The ages of the New England Patriots were reported as integers and may be considered discrete. However, age can also be considered continuous. For example, if ages are not rounded to the nearest year, then any of the following ages are possible. You could be 26 years old, 26.01, 26.000009, and etc. So if they're not rounded by year and not countable, then they could be considered continuous. This diagram here, shown in number 10, is from your textbook on page 250. Illustrates the difference between discrete and continuous. It's pretty helpful to think about it. So discrete, you can count. You might be, okay, 1, 2, 3. It's like a staircase. You're either at 1 or at 2, okay? Whereas a ramp is a continuous incline and not able to count. And so if you think about it that way, it's helpful in figuring out whether you're looking at a discrete or continuous variable. The distinction between these 2 types of numerical and variables is important because it will determine how we can display the probability distributions. Okay, so again, we need to classify our variables in order to properly display them. The probability distribution of a discrete variable can be displayed either as a graph or a table. The probability distribution of a continuous variable can be displayed as a graph, but not as a table where each value is listed. Instead, you'd have to have ranges of values or subsets of the values. Okay. So the following is a sample distribution of the heights of a sample of mothers. The source is Galton's mother and daughters data set used in Sanford's Weisberg's Applied Linear Regression 3rd edition. These heights are considered continuous since the heights are not rounded to the nearest inch. So there's any of the following heights are possible. You could be 62 inches, 62.01 inches, 62.000009 inches, etc. So you get the idea. They're not rounded. We're looking at continuous data. So this distribution gives us the heights of women in a sample as well as the relative frequency of women for each height range, okay? Because we have continuous data, we have intervals of height ranges. If we present this information in table form, there's too many individual heights to list, so we instead provide the frequency for each range of heights. So we can see the table below. If we look from 55 to 60 inches, we had 194 mothers that were between 55 and 60, and their relative frequency then would be 0.141. So how can we find the probabilities for continuous outcomes? As we saw above, we can't list all the possible values we might see, but we can list the range of values we might see. So we can find the probability that a particular observation is between two given values. So use the histogram. Use the histogram to find the probability that a randomly selected mother has a height between 60 and 65 inches. So between 60 and 65 inches, hard to fit this whole thing on our screen. 60 inches is here, and 65 is here. So the probability that we choose a mother that's between 60 and 65 means that we would need to sum up all of these relative frequencies. So if we sum these up, we would have 0.12 plus 0.15 which is equal to 0.71. In other words, about 71% is the probability that a randomly selected mother has a height between 60 and 65 inches. Just to note that in StatCrunch, you are able to select your bin widths for these histograms. So you can set your own bin width, and you can choose to get the relative frequency by opting for that in the menu. And this number here, this relative frequency, is actually the area of this rectangle, okay? So really when we calculate the probability here by adding these all up, we're actually calculating the area of these rectangles. Okay. So is this probability the same as reported in the table? So here is a probability distribution in the form of a table, and yes, it is very close. So here in the table, 55 to 60. Oop, I just circled the wrong one. I'm sorry. 60 to 65 is 71.6%. And so the table, when you create this in StatCrunch, you're not able to actually choose the ranges for each of these intervals. StatCrunch does that for you. What is the sum of the relative frequencies in the histogram? So if we add up all the frequencies in our histogram above, so 0.001 plus 0.01 plus 0.02, you keep adding them all up, plus point. This comes out to be very close to 1. So the idea is that when we're looking at a relative frequency histogram, that the area under the in the histogram totals 1. So this is number 14. Now a coffee shop Manager is interested in finding the probability that a customer will wait less than 2 minutes to be served. The following probability density curve, which is a model of the histogram of wait times, okay? So they just decided on a curve to model what the histogram would look like. So we have this nice smooth curve to work with. This probability density curve shows that the probabilities for this continuous valued random experiment as areas under the curve and has the area between 0 and 2 minutes shaded. So down here, we're looking at the shaded time is just telling us what this area here is the probability that a person will have to wait between 0 and 2 minutes. So just like we saw on the previous slide where the area under the whole histogram, the area of the histogram is 1, the area under a probability density curve is also 1. So area under curve is 1. So using this diagram, we can estimate the probability that a customer has to wait less than 2 minutes to be served. So to me, this looks like that this shaded area is less than 50% of the total area, right? So let's say it's about 45%. So the probability that someone would have to wait under 2 minutes is about 45%. Use this diagram to estimate the probability that a customer has to wait more than 2 minutes to be served. And so that's actually the complement of what we just did. And so we could look at it as like 100% minus 45% is equal to 55%. So there's a 55% chance that a person would have to wait longer than 2 minutes. In practice, it is often difficult to know the exact shape of a distribution. For instance, how did the coffee shop manager know that the probability density curve given above was correct shape? The manager hopes that the probability model resembles the histogram of actual wait times for her customers, but can't be sure. If the manager compares the predictions from the model to the actual frequencies from a sample of customers, then she can determine how good the model's predictions are. So if she actually did a study, collected some data, drew a histogram, she could see how well this curve fits her actual data. And then she would know whether that is a good model or not.